students. Today we will discuss about some previous problems in work, energy and power chapter. So here this is the first problem. In this problem, a particle moves in one dimension from rest under the influence of the force that varies with distance traveled by the particle as shown in the figure. So now the kinetic energy of the particle after it has traveled 3 meters. So in this problem, so some diagram are there, that is here force along y-axis in newtons and distance along x-axis. So in this case, we can find out the kinetic energy of the particle after it has traveled 3 meters. Okay. Now we can solve this problem. So here in this problem, it is a displacement, force and displacement graph. So therefore, the area under force displacement graph gives work done. So by applying work energy theorem, W equal to kinetic energy, that is the change in kinetic energy. So in this case, you can find out the work done. So therefore W equal to, so here the area under the force and displacement graph gives, it means work done. So here this area, this shaded area is, you can find out the work done. So here this shaded area is treated as two parts. So this one part, this one two part. So here this is the first part, this is the second part. In the case of first part, the area of the rectangle. So here area of the rectangle is length into breadth plus second part area is, it is a triangle. So area of the triangle of base into height. So now W equal to, here length is 3 minus 0, that is the 3. Here breadth is 2 minus 0, 2 plus of base. Here base is 3 minus 2, that is the 1. Its height is 3 minus 2, that is the 1. So therefore W equal to 6 plus 1 by 2. Okay. So that is 13 by 2, that is the 6.5 joules. So we know that according to work energy, the work done is equal to kinetic energy. So here kinetic energy is 6.5 joules. So this is the answer. Next problem number 2. So in this problem, a uniform cable of mass capital M and length capital L is placed on a horizontal surface such that its 1 by nth part is hanging below the edge of the surface. To let the hanging part of the cable up to the surface, the work done should be. Okay. Now in this problem, Total mass of the cable is capital M. Total length of the cable is capital L. So here a horizontal table is there. Now 1/nth part of the chain is hanging. So in this situation 1/nth part of the chain is hanging. That means total length of the chain is L by N. So L by nth part of the chain is hanging. So therefore the mass of the hanging part of the cable small m equal to capital M by N. So here capital M means total mass of the chain, but in the edge of the table 1/nth part of the chain is hanging. So total, so the mass of the hanging part of the cable is M by nth. Okay. Now in this situation the center of mass of the hanging part of the chain is half of the L by nth. So here this is the center of mass. So here center of mass of the hanging part is, that is the displacement of the center of mass. Center of mass, that is H. Here H equal to L by nth by 2. So that is the half of the L by nth. So that means L by 2n. L by 2n. So now the hanging part is pulling upward to try the lift on the horizontal surface. Then the work done is it is a potential energy. So the equation of the potential energy is mgh. So here mgh, here small m means capital M by N into here G into here H is displacement of the center of mass of the hanging part of the cable, that is L by 2n. So therefore mgl by 2n square. This is the answer. Problem number 3. A time displacement force F equal to 60 acts on a particle of mass 1 kg. If the particle starts from rest, the work done by the force during the first second will be. Okay. So in this problem, if we consider body of mass small m, that is the 1 kg. Its mass is 1 kg. A force F is acting on the body. So it is initially at rest. Then work done by the work done on the particle in first second. Okay. So in the situation given force equal to force equal to 60. Now according to Newton's second law, F equal to ma. So A equal to F by m. Here F is 60. Here mass of the body is 1 kg. That is the 60. Okay. Now we know that acceleration means the rate of change of displacement is known as acceleration. So therefore dv by dt equal to 6t. So therefore dv equal to 6t into dt. Now in the above equation integrating on both sides. So therefore integral of dv, here limits 0 to v. Next one, here integral of t 0 to 1. So here initial time is 0 second, final time is 1 second. So therefore in this case dv, that is the v, integral of dv equal to v equal to 6 into t square by 2. Here limits 0 to 1. So therefore v equal to 6 into 1 by 2. So here 3 times. So velocity equal to 3 meter per second. So in this case work done is equal to kinetic energy. So therefore work done equal to kinetic energy. You know that the equation of kinetic energy is half mv square. Here half m means mass of the body 1 kg. Here v is 3. So 3 square. So therefore w equal to, so 9 by 2, that is the 4.5 joules. This is the answer. Right on. Next problem, problem number 4. An alpha particle of mass small m suffers one-dimensional elastic collision. Its collision is elastic with a nucleus at rest. Here nucleus is at rest of unknown mass. So here there is no mass of the nucleus because we can find out the mass of that nucleus. Okay. It is scattered directly backward. That means alpha particle is scattered directly backward, losing 64% of initial kinetic energy. So it loses 64% of initial kinetic energy. Then mass of the nucleus is, okay. So we can solve this problem. Here this is the alpha particle, its initial velocity is u. So here this is the nucleus. You can consider its mass is capital M. So now you can find out the mass of the nucleus. So it is at rest. It is at rest. Now this alpha particles is collide with the nucleus, then it is rebounds in backward direction in this way. So mass of the nucleus is small m in backward direction. So this is the, here v1 is the final velocity of the alpha particle, u is the initial velocity of the alpha particle. Next mass of the nucleus is capital M. So but here initial velocity of the nucleus is 0. So here alpha particle is collide with the nucleus, then the nucleus final velocity is, that is the v2. Okay. In this case, according to law of conservation of momentum, law of conservation of momentum, mu is equal to, so initial momentum equal to final momentum. Here final momentum is 2, that is final momentum of the alpha particle, final momentum of the nucleus. So therefore m v1. So here opposite direction of the nucleus. So that means minus m v1 plus capital M v2. This is the momentum of the nucleus. This is the final momentum of the alpha particle. This is the initial momentum of the alpha particle. So this is equation number 1. But in this given problem, it is a elastic collision. It is a elastic collision. So coefficient of resistivity equal to V2 minus, so here minus of V1 by U1. So that is a U. So therefore V2 plus V1 by U. Here V2 is the final velocity of the nucleus, V1 is the final velocity of the alpha particle, U is the initial velocity of the alpha particle. So according to elastic collision, coefficient of resistivity is 1. We know that. So therefore 1 equal to V2 plus V1 by U. So therefore U equal to V2 plus V1. V2 plus V1. So therefore V2 equal to final velocity equal to U minus V1. U minus V1. Okay. Next. So here final kinetic energy of the alpha particle is equal to 64 times of the 64% of the initial kinetic energy is losses. So the remaining part of the kinetic energy, that is the final kinetic energy, that is 36% of initial kinetic energy. So that is the alpha particle. So therefore Ke final equal to 36%, 36 by 100 into initial kinetic energy of mu square. So in this equation, final kinetic energy means of mv1 square equal to 0.36 into 1 by 2 mu square. Here of cancel, m cancel. So v1 square equal to, so that means v1 equal to root over 0.36 u square. It means 0.6 u. Here v1 equal to 0.6 u. So therefore this value substitute in equation A. So therefore V2 equal to U minus V1. V1 means 0.6 U. So U is common. 1 minus 0.6, that means 0.4 U. So therefore final velocity of the nucleus is 0.4 U. Okay. Now these values are substituted in equation 1. So here V1 is, here can write that V1 is 0.6 U, V2 is 0.4 U. So here these values substitute in equation 1. We get in equation 1 mu equal to minus m into V1 plus capital M into V2. So in this case capital M V2 equal to mu plus mv1. So here common is m u plus v1, u plus v1. So now mv2 equal to m into u plus, here v1 is 0.6 u. So therefore mv2 equal to mu into 1 plus 0.6. That means mu into 1.6. Now you can find out the V capital M is equal to mu into 1.6 by V2. So mu into 1.6 by, here V2 means 0.4 U, 0.4 U. So here U cancel. So I can multiply in 10 by 10, 16 by 4, that is 4 times. So that is 4 M. So here mass of the nucleus is equal to 4 times greater than the alpha particle. So here capital M equal to 4M. This is the answer. Thank you.